Hello everyone and welcome to this week's lightweight Java game library 3D game tutorial, and this week we're going to be programming a skybox. So as I'm sure most of you already know, a skybox is just a simple box with a nice texture of the sky all around it. The box contains all of the visible world and it follows the camera around, meaning that the camera is always in the center of the box and it can never reach the edges of the skybox. A lot of the stuff that we're going to be doing this week is stuff that we've already covered, so I'm going to try and keep this episode as short as possible by providing you with the code for any of the stuff that we've already done before. But there is one new concept that we're going to be using this week, and that is CubeMap textures. So up until now, we've only ever used simple 2D textures like this one here. But cube maps are textures in the shape of a 3D cube, where each side of the cube is basically a 2D texture. But this whole thing counts as just one texture with 6 sections. Cube maps can be used for a number of things, but obviously they are perfectly suited for creating a skybox. Instead of using 6 individual textures to texture the skybox, we can just use one cube map texture. We'll create the cube map from 6 separate images, but it will be stored as one texture. This means that before we render the skybox, we just have to bind that one cube map, and then we can render the whole skybox. One other thing that's slightly special about the cube maps is the way that they have to be sampled. Usually, to sample a texture, we provide a 2D texture coordinate, and the color of that point on the texture is returned. However, this obviously won't work with a cube map, seeing as it's not a simple 2D texture, it's a 3D cube. So to sample a cube map, we have to provide a 3D direction vector. The direction vector points from the center of the cube to the point on the texture that we want to sample. For example, a direction vector of 0, 1, 0 would point directly upwards, and therefore would sample the pixel in the center of the top face. A direction of 1, 0, 0 would sample the center pixel on the right face, or a direction of -1, -1, -1 would sample the back left bottom corner. So we can sample any point of the cube map by using the relevant direction vector. And the best thing about this, and the reason why cube maps are so perfect for skyboxes, is that the vertex positions of a cube can also be used as the direction vectors for sampling the cube map. So we won't be needing any texture coordinates this week, we'll just create a cube model from a load of vertex positions, and then those vertex positions will double up as the direction vectors used to sample the cube map in the fragment shader. Unfortunately, I couldn't find a way to create cube maps using the Slick Utils library, which is the library that we've been using so far to load textures, so we'll have to download a new texture loader called PNG Decoder, and there's a download link for it in the description of this video. Once you've downloaded it, just put it wherever you've put the lightweight Java game library jars, and then in Eclipse, just right click on your project, go to build path, configure build path, and then in the libraries tab you need to add jars, and then find the PNG Decoder jar. You're also going to need to add this very simple texture data class into your textures packages, and you can either copy this down now or you can download it from the description of this video. As you can see, this is just a very simple data structure that holds the decoded byte data of an image and also the height and width of that image. Finally, in the loader class, you'll need this method here that uses the PNG decoder to load up an image into a byte buffer, and then it returns it as a texture data object, which is the class that I just showed you, and it also stores the width and the height of that image. You can also copy this method from the downloadable code provided in the description. So we now have a way to load up PNG images into texture data objects, which is great. So now let's create a method that can load up a cube map to OpenGL, and this is going to return the ID of the cube map texture so that we can bind it when we're rendering the skybox. This method takes in a string array which contains the 6 texture file names, the 6 textures that we're going to use to make up this cube map. So in the method, the first thing we're going to do is we're going to generate a completely empty texture by calling glGenTextures, and that returns the ID of that empty texture so that we can now use it. The first thing we're going to do is we're going to bind that texture so that we can do stuff to it, so that we can store data in it. So we've activated texture unit 0, and now we're going to bind the texture to that text unit by calling GL bind texture. Usually when we call this, we put in GL texture 2D, but this time as the first parameter we're putting in GL texture cube map to indicate to OpenGL that this texture is going to be a cube map. So now we're going to loop through all of these 6 textures and we're going to load up each one into the cube map. So we'll loop through them all, and the first thing we need to do to each texture is to load it up into a texture data object, so we have the data of that texture available to us so that we can load it into the cube map. So we're going to call the decode texture file method. All of my textures are going to be in the res folder and they're all going to end in .png. So in this array of strings that this method takes in, we just need the actual names of the textures. Then we're going to load up the texture data into the cube map by calling GL text image 2D, and this takes in a huge amount of parameters. The first I'll talk about in a minute. The second one is just the level where you put 0. The third one is the format that we want to store the data in, and that's just going to be GLRGBA. Then we need the width of the texture, which we'll have in the texture data object, as is the same with the height, so data.getHeight. The border, we don't need a border, so put 0. Format, again the format of the data is in RGBA. The data type, the type of the data is bytes, so we put in GL unsigned byte. And then the final parameter is the actual texture data, which we have in the texture data object, data.getBuffer. So that first parameter of the method is where we indicate which face of the cube map we want to load the texture data to. There are of course 6 options for this, one for each face of the cube, and I've listed all of those options here. But of course we want to be able to loop through the faces so that we don't have to call that method 6 times in our code. And luckily we can do this because these are all actually just ints, and their values are consecutive. So in our for loop we can just put the first option, which is GL texture cube map positive x, and then add I, so that each iteration of the for loop stores the texture data in the next face of the cube map. So basically we're iterating through all of the faces and we're storing the relevant texture data in each one. Therefore we must remember that the string array of texture file names must be in the same order as these int constants. So the order in which we specify the texture file names has to be first the right face of the cube map, then the left face, then the top, then bottom, then back, and finally then the front face. So let's now put that in the code. So the first parameter of that GL text image 2D method is going to be, as we said, GL texture cube map positive x, because that's the first of those int constants. And then for every iteration we're going to add 1, or so we put plus I, so that it iterates through all of the faces of the cube map. Then after the for loop we need to call these 2 methods to set the mag and the min filter. And we talked about these a bit in the MIP mapping tutorial, but basically all this does is to make the texture appear smooth. And if you want to know more about these 2 settings, I've put a link in the description to a very interesting website that shows you all about the different parameters that you can set for textures in OpenGL, so give that a read if you're interested. The final thing that we have to do is just to add the texture ID to the list of textures so that it gets deleted when we clean up the program at the end when the game closes, and then we're going to return the texture ID. While we're in the loader class, we also need to alter this load to VAO method here, the one that we're using for loading the GUI positions. At the moment it only works with 2D positions, but we also want to be able to use it for 3D positions this week. So let's make this method take in the number of dimensions that we want it to use, so that it can be used for loading up GUI quads and also 3D skybox cubes. So just replace the 2 here with dimensions, and here as well. And of course that's going to mess up the code in the GUI renderer, so just go there and add in a 2 to indicate that these are 2D vertex positions. So let's now go ahead and create a Skybox package in our project, because we now need to create a new rendering system specifically for the Skybox. So like always, we're going to need a new vertex and fragment shader, and then a Skybox shader class and a Skybox renderer class, just like we have for entities, terrains and GUIs. The shader code is extremely simple, as you can imagine, seeing as we just want to render a simple textured cube. So you can download the shader code from the description of this video and put the vertex and fragment shader code files into your Skybox source folder. Then just refresh the package in Eclipse and you'll be able to access the code. So let's have a quick look at what we've got here. The vertex shader is super simple and nothing that we haven't ever done before. Notice that we're not using a model matrix or transformation matrix here, because we're never going to need to scale, rotate or move the Skybox. So we just have the projection and view matrix here like we always have. You'll also notice that the texture coordinates are a 3D vector instead of a usual 2D vector, because as I explained earlier, we're going to be sampling the cube map using a 3D direction vector and not a 2D texture coordinate. As well as that, you can see that the 3D direction vector is just set to the vertex positions, because as I showed you earlier, the vertex positions are exactly the same as the direction vector we'd want to use to sample the cube map. The fragment shader is the simplest shader code ever. We just take in the 3D direction vector for sampling the texture, and then we use the texture method as always to sample the cube map texture. Of course, the difference is that this time we're using a 3D vector to sample it, and we're using a sampler cube this week instead of the usual sampler 2D for obvious reasons. So moving on, let's now create a Skybox shader class in the Skybox package, and we can also create a Skybox renderer class as well. I'm not going to make you program the Skybox shader class because we've done this sort of stuff so many times already, so you can just download the code for this class in the description. So have a quick look through the code here. But really by this stage it should be very obvious to you what all of this code in this class does. The Skybox Renderer class, however, is going to have some new stuff in it, so we're going to program this class together. The first thing that we need to do is to determine all of the vertex positions of our Skybox cube so that we can load them up into a VAO. And you'll be very relieved to hear that you can copy these vertex positions from the download link in the description. You can change the size value here to make the Skybox cube bigger or smaller if you want, but it's probably best just to keep it as it is for now. So at this point in the video, you're going to need to get the 6 images that you want to put into your cube map texture, and you can download the Skybox images that I'm going to be using from the description of this video. Make sure that you put them into your res folder and give them some relevant names so that you can remember which image goes on which part of the cube. There's also a link in the description to a site that has loads of possible Skyboxes that you can use instead. So back in the Skybox renderer, the first thing that we're going to do is to create a string array of all the texture file names, those 6 texture files that we're going to be using for the Skybox. And we have to make sure that they're in this specific order, the same order that we were talking about earlier, the order that those OpenGL constants were in. So make sure that you specify the right, then the left, then the top, bottom, back and front textures of the Skybox, and it has to be in that order. Then we also need to have a raw model, which is going to be the actual cube model for the Skybox. Then of course we have the texture ID for the cube map, and we also need a Skybox shader. So let's now create a constructor for the Skybox renderer, and this is going to take in the loader so that we can load up the texture and the VAO, and it's also going to need the projection matrix because we're going to load that up to the shader. So the first thing we're going to do is to create the cube, and the cube is going to be created by calling the load to VAO method in the loader, and we put in those vertex positions and we indicate that they are all 3D positions. Then we need to load up the cube map texture by calling that method that we made earlier, and that takes in that string array of texture file names. And then the shader we can just create by calling the constructor for the Skybox shader, and then straight after that we're going to start the shader, we're going to load up the projection matrix to it, and then after that we're going to stop the shader again. So we need one more method in this class, and that is of course a render method. And I'm going to go through this pretty quickly because it's all stuff we've done before. So the render method is going to take in a camera because we're going to need that for the view matrix. So to get started, we start the shader, we load up the view matrix, which takes in the camera. Then we need to bind the VAO of the cube. So we call GL bind vertex array, and we put in the VAO's ID, which we can get by doing cube.get VAO ID. Then we have to enable attribute 0 in that VAO because that's where the positions are stored. Then we need to bind the texture. So as always, we'll activate a texture unit. So we'll activate texture unit 0. So GL texture 0, and then we're going to bind our CubeMap texture to that active texture unit. So here we would usually put GL texture 2D, but this time we're going to put GL texture CubeMap because of course it is a CubeMap, and then we put in that texture ID. And now we can actually render the skybox by calling GL draw arrays. This needs to know the mode, and we're just going to be using GL triangles. The first index is just going to be the 0th index, and we want to render all of the vertices. So cube.get vertex count for the number of vertices that we want to render. And now we just unbind everything, so disable that 0th attribute in the VAO, and then unbind the VAO by calling GL bind vertex array 0, and then we stop the shader because we are done. So let's now go into the master renderer, where we're going to set up a Skybox renderer so that we can use it to render the skybox. So let's do that. The master renderer constructor is now going to need to take in the loader, because of course the Skybox renderer constructor also needs to take in the loader. So now you can call the Skybox renderer constructor to create an instance of the Skybox renderer, and that takes in the loader and the projection matrix. Quickly into the main game loop, we just need to give the master renderer the loader so that that works. Back in the master renderer, we now need to call the render method, and we're going to do that after we've rendered everything else. So after you've rendered the terrain, you're going to call the Skybox renderer.render method, and that takes in the camera. And we can go ahead and run that now, and hopefully we should be able to see some nice sky, and we can, but it's not working exactly how we would want it to, because as you can see, if I keep walking, I can actually reach the edge of the skybox, and I can even go outside it, which obviously isn't really what we want. So what's going on here is that all we've done so far is to create a textured cube model, and we've rendered it in the world. Seeing as we haven't used any transformation matrix or anything, this giant cube is just rendering at the origin at 0, 0, 0, and it's just staying there, which obviously isn't what we want. So we need the skybox to follow the camera around, so that the camera always stays in the center of the box. We could do this by creating a transformation matrix for the skybox, and then setting it to the camera's transformation, but there is actually an easier way. If you remember all the way back to episode 8, you'll remember that I explained that there isn't actually a camera at all, and that we just simulate the effects of a camera by moving the whole world in the opposite direction using the view matrix. So if we were to remove the view matrix, then the skybox wouldn't move at all in relation to the camera. So in the Skybox vertex shader, let's try removing the view matrix from the calculation, and now let's run that to see what happens. As you can see, the skybox is now completely unaffected by the camera moving, and stays totally fixed on the screen. But this isn't quite what we want either, because we still want the skybox to rotate when we rotate the camera like this, but at the moment it's completely fixed in place. So we still want the view matrix to apply a rotation to the skybox, but just not a translation. So let's put the view matrix back into the calculation here, and then in the Skybox shader class, we can actually edit the view matrix before we load it up. In a 4x4 matrix, the last column determines the translation. So if we just set this translation to 0, 0, 0, then the view matrix won't cause the skybox to move in relation to the camera. So let's do that, and now run that, and there we go. Everything now works very nicely. The one thing that you might notice is that the fog doesn't work quite as well as it used to, because in the past we just had the faraway objects blending into the colour of the sky, but now the sky is more than just one plain colour, so this is a bit more complicated. But that's something that we'll fix next time, so until then you can just set the fog colour to something that matches the skybox as closely as possible, so that the problem isn't as noticeable. So that is going to be it this week. I know I was going pretty fast this time, but by this stage I'd hope that you'd already have a pretty good grasp of setting up shaders and creating and rendering VAOs and stuff, so hopefully it wasn't too much of a problem. Don't forget to check out yesterday's devlog video if you haven't already. There were some exciting new mobs in the game this week, and there's a link to that video on the screen now. Do stay in touch via my social media sites, including my new Tumblr page. Links are in the description below. But yeah, thank you guys very much for watching this video. Do subscribe if you haven't already. Have a lovely week, and I will see you all next time.